We are talking about stack-based breadth-first search tree traversal. If we see breadth-first search tree traversal, it means that a tree would be, first it would be searched at the root node, then level 1, level 2, level 3, level 4, like this. That is breadth-wise. We have to parse the tree or print the tree. So typical solution for a breadth-first search tree is maintaining a separate queue. If tree is of entry is 1 billion and one node contains kind of 4 bytes, then 1 billion size nodes are there, and 4 byte one int size is also, if it is for one node, then 4 GB space is required for the heap. So tree, along with a tree, we need to maintain extra heap or extra queue, and in the queue, the algorithm is that when you parse a node, then all its children you have to push in the queue in the FIFO order, first in, first out. After that, so it's a kind of, if you encounter a root node, you can place in the queue, and you start popping up the queue. So this is the FIFO, first in, first out. So root node came into the queue, you pop the queue, and then you place all its children in the queue. Now first one, that is the first children, first level, first children. If you pop it out, next all its children you have to place in the queue. This way, actually, you guarantee that at a particular level, if you are finishing the last item, all the items in the next level are in the queue. So only idea behind it is, if I am at root level, the next level is inside the queue. If next level end I am popping out from the queue, then third level full is inside the queue. So this way it will actually print breadth-wise. But there are two problems. One is you have to maintain a queue, and it can be dramatically very high, and sizes can be very high. Like I said, if it is 1 billion node, and kind of if it is a binary tree, then it is a little nice, and if it is not a binary tree and complexity is more, then the size would be very big. Typically the last level full size, at least that much size it should be there. So it will be directly proportional to the size of tree only. I think in binary balanced tree it would be half of the size of tree. Again, it will be very big. That is, space is one problem. Second problem is you have to keep writing in the queue. So write speed is very less. So write speed is typically 10 times less than read speed. So if you keep writing full queue in the full tree in the queue, and then reading, and then again keep writing, so this is not a clever solution. So that here we comes as a stack-based tree traversal, breadth-first tree traversal. So in a stack-based breadth-first tree traversal, we don't maintain any extra queue at all. So where we rely upon is, we'll go for a kind of recursive function, and if I have a 32 layer, if I have a kind of 4 billion nodes, 4 billion nodes, then it will be of 32 level. So maximum it will go to 32 recursion. So that is completely acceptable. One recursion, if I have 2-3 parameters, then 4 bytes, or it will take in 32-bit machine. So 32 into 4 bytes into, if I have 3 entry into menu function, or in function argument 3 parameter in the function, then 4 3s are 12 into 32 bytes. So that is completely acceptable. 32 into 48. That much I think it will come to 1K size maximum. So 1K is far less than 4 GB or something like that. So it is highly, and second thing is it would come in a stack only, so it will be high speed. No need to write in the queue so many times. So that is another gain. So how it works, if we see the logic behind it, then we maintain a two pointer. One sits at a level, like we start at level 1, that is the root. My pointer will also start from the root, and pointer will come with a expectation that I have to print at level 1. Finds it prints the node. Then my level will be 2, that is the second layer, and my pointer will start from the root. It goes to its left child or first child, and it finds that level what it wants. It meets the level. It would print it, come back, go to its next child, print it, then come back, and finally it will come back to root, and then it will start again, and it will print all the nodes at level 1. Then our level pointer would go down at level 3, and it will start from the root again, and it will traverse till it finds the level 3, print it, go back, again traverse through another children pointer and print it. So this way we print the third layer. Like that we will take the layer pointer to 4, 5, 6, 7 like this, and layer pointer and the beginning pointer. When both matches, we print them. Quite simple, and algorithm is a little bit kind of recursive, so it requires more attention to be taken care. Otherwise, it doesn't require any heap, any queue or something like that. So, in a kind of balanced kind of tree, it is a boon. If we see the speed, it is unmatchable. It is it passes the tree at very high speed because it does not write each node in the queue or something like that. So that we'll see stack based tree traversal, breadth first tree traversal, how fast it is and how. We are in discussion for stack based breadth first search tree traversal. We'll see first the traditional way, that is queue based. Okay, so this is traditional way, queue based BFS. So traditional way of queue based BFS, it is first root node is enqueued. Okay, so first root node is enqueued, and there is a separate queue for it, and root is getting enqueued. This is the idea. Now we will start by dequeuing the root node. When we dequeue the root node, this is root node. First we enqueue the root node. Now we are dequeuing the root node. When we are dequeuing the root node, we are pushing all its children in the queue. So all three are in the queue. Now we are dequeuing the next one in the queue. While doing so, we are pushing all its children in the queue. Now we'll dequeue this, and we'll push these two, then we'll dequeue this, and we'll push all these three. Now we'll dequeue this, push its children like this. Now when we dequeue this, we push all its 3 children, but if we dequeue a node in a particular level, that is the end node, now it is guaranteed that all children in the next level is inside the queue. If we are here, then it is guaranteed that all its children are in the queue. If we are here, then all the children in the next level are in the queue. So this is the idea behind queue-based BFS. We dequeue the queue and push its children, dequeue the queue, push its children, dequeue the queue. When we are at the end of a particular level, all the children at the next layer is inside the queue. So this is a queue-based BFS. Now we'll bring in a stack-based BFS. So this is a stack-based BFS. So this is stack-based BFS. In stack-based BFS, there are two pointers. So there are 2 pointers. One pointer is level and one pointer is target. This is how it starts. And at the beginning, level is 0 and target is 0. It would print the root node. Now next time it enters the function, so it's a recursive function. Next time it enters the function and target is set to 1, where another pointer is at level 0. Since it is not matching the target, it will now traverse the tree from its first children and see if it matches. It matches. Target is 1, level is 1. It would print the node. Now it would go back and try its next children, that is this, and see if it is matching. It would print it. Now it will go back and try its next children, see if it is matching. So it would print. It's very simple. Now target is number 2 and another pointer would start from the root node. Now it will go one by one. It will go to left children and it doesn't find the target equal to level. It will go again and it finds. It prints. Now it goes back and it try the next children and it prints. Now target is same. Target is at layer 2, layer 3 or target layer number 2 if we are starting from the 0, 0, 1 and 2. So now level is 1. It will try the next node. So it tried the first one, matches, then tried the second one, it matches, then it comes back, then it tries for the next children. There is no next children. So it will come back to its parent one. Then it will try the next children. So it is there. Then it will try the first children. It matches. Come back, try for the next children. It is matching. Come back, then there is no next children. It will come back. Then try for the first children, like this. Now target is set to third layer. Now it would start from the root node again. Left, no matching. Left, no matching. It matches. It prints it. Comes back, try in the next one. It prints it. Now there is no next children, so it comes back, it tries here, then there is no children, it comes back, then comes back here, then comes back here, and it prints this. comes back, it prints this. It prints it. Okay. What is good thing about this approach is there is no extra queue that need to be maintained. And for if target is 3, then 3 recursion of the function is required. So in a balanced kind of tree, then layer level would be very less. Even if it is 4 GB size, then level would be around 32. So 32 level is nothing. And size of the stack is just mere the 1 or 2 pointer. So if it recurs 32 times also, 32 into 2 into 4 on 32-bit machine, that much it should take. So it's nothing. It's in, I think it would come in kilobyte. So it is far less than the queue-based BFS. So these are, we can start the animation. So probably we'll go to the beginning and we can start the animation. So it is dequeuing and pushing in the queue one by one, and this is how it is printing the node. That is the idea. Here also we can start. Probably we can go to the beginning and we can start. Okay, so level is changing, target is changing, and it is doing the stuff. Here also we can start from the beginning. So queue based, it is a queue, it is pushing and it is pulling. In stack based there is no queue, and level is changing and target is level and target is changing. So target is changing. If level matches to the target, it is printing. Otherwise, it is not printing. Good thing about a stack based is there is no write operation in the queue and it is quick. Whereas queue based, it is extra memory is required, heap memory, and it is slow if tree is very big. So that is the scenario. This is already published, queue based and stack based BFS. It need to be searched as stack based BFS. And here it prints the algorithm also. Algorithm program is placed, and it is kind of one while loop, and then this is a recursive function, print tree. Okay, so it is a while loop in one function that starts, begins it, and passes the target one by one, more and more and more. And this guy print tree, it recurs and it tries to match the level and the target. That's it.